Hello everyone. I hope you're not too hungry and too tired for this last talk of this section. But today I'm going to talk about what I think is a very important subject when it comes to any kind of analysis, and it's about analytical precision, in this case specifically of IgG glycome profiling. So in today's lecture, I would like to go through two of our papers that we published recently. I would also like to give you an overview of our method so that you have a basic idea how the method is performed and what are the potential sources of variation. Then we will go through our paper outlining automation of this method and how we tested with in-run precision and how we compare the two methods. Then we will go through some of the things you already saw from Professor Lautz's presentation, talking about a bit about glycan stability, but we will also touch on other types of precision. And finally, I will give my conclusions and I will tell you what I would like to see happen in the near future for glycomics. Let's begin. So the brief overview of our methods. So what we do in our high throughput methods. So we basically start from 25 microliters of plasma. We isolate the protein of interest. The protein of interest in IgG glycome profiling is, of course, IgG. We have to denature the protein. We have to release the glycans, label the glycans, and purify them from all possible impurities which may affect final analysis, and we can analyze it, or our methods analyze it using UPLC and using CGE. So what is imprecision and why is it critical? Why is it important? So whenever you're evaluating method, I'm very sure that most of you, or if not everyone, is aware that it's a critical part of the method you are testing and you are developing. And it's important not just because it tells you that what results you are getting every time you run a test, but it also can tell you when you're doing multiple runs, when you're doing it with different operators, with varied conditions. It can tell you how your method is performing on a single day or across multiple days. And for example, when we look at our method outlined here, we can see some of the potential variations I try to outline. So differences in pipetting. If you have different operators pipetting, of course, not everyone will pipette the same way. Somebody will be more careful, somebody will be less careful. Then you have variation in materials used. Not every plate is the same. So there is difference from one plate to another. Of course, there are differences even greater between different manufacturers, and if you're using different manufacturers, you have to make sure that you take all of that into calculations. Then you have variations in solutions. For example, in our laboratory, some of the solutions are prepared manually. And of course, you cannot make the same thing over and over again, especially if you're doing it manually. So there are some variations being introduced that way into our methods. But even the industrially prepared ones, we can see variations between from batch to batch. Also, small variations in temperature or pH, which happen on a random basis, also can introduce sources of variation. So as we can see, there are a lot of potential sources of variation, and we have to control for them some way. And so in order to try and alleviate this some way, we developed an automated method. This paper was published in Biochemia Medica, and it's important to remember this Medica part because it's going to be very important later on. What we tried to do in this paper, we tried to replace the manual processing of the glycans with an automated one. We used Tecan Freedom Evo 200 combined with A200 positive pressure units. And we created this method for UPLC, the one which was reported in this paper. So the first thing we did, as you can see outlined in this table, we tried to compare the two within-run precisions, or repeatabilities, as is it often called. What did we see? As we can see, comparison of the two methods, both methods are very, very similar. So There is slight difference, and because of this setup of this test itself, so for the setup we used only 2 plates. It was 78 samples from Croatia cohort, which were chosen at random, so there was no prior choosing of people who would be involved, and also we used 32 replicates of our standards, which were used as technical replicates, which were used to generate this table. And as we can see, in part, the automated method performed slightly worse, but not in all peaks. In some peaks it did better, in some peaks it did worse. What it's very important is the sialic acids, which had pretty high variation for both methods, and especially for Glycome peak 22, which is highlighted in red, which is the only peak that was over 16%. All peaks, as you can see, are pretty steadily under 10%. Smaller peaks usually have higher variation. This is partly due to more noise coming in, because if you have a smaller peak with a smaller relative abundance, noise will have greater effect on it and we will have greater variation. But even when we have, for example, here 10.8%, we can see that it's a standard deviation of only 0.02% of relative area. So these results were very promising. And if you're not really people of tables, I have also prepared a graph showing this visually. So the bars are representing the relative areas of each of the peaks. You can see automated peaks are in blue color and manual peaks are in red color. These black standard error bar are representing the plus-minus standard deviation. And as you can see, this standard deviation really contributes very little to the overall height of the average peak, and we can see that the precision is quite high. Next, we wanted to compare these two methods using a statistical method. For this case, we used passing bubble regression. It is a very common method to use in clinical setting, in clinical laboratories, and this is particularly because it's useful because it doesn't assume a normal distribution of errors. It also is very resistant to outliers. It can evaluate both intercept, so it can evaluate constant error, and it can evaluate systemic error. And when we compared our two methods, we noticed that majority of the peaks, so half of the peaks, showed no difference between the methods. 8 peaks showed constant errors. Constant errors are usually easy to control for, and you can easily correct them using statistics, but we also had 4 peaks with proportional errors, and in part those were usually smaller peaks, and one of the biggest offenders here was the peak 24, which had the largest proportional error. Next part would be next big development or important development of this paper was developing of acceptance criteria. Acceptance criteria is something that is regularly used in clinical laboratories, not so much in research. And given the fact that this journal we were publishing in was clinically oriented, they asked us to develop acceptance criteria. Acceptance criteria can be developed on or determined based on several factors. Some of the most common factors are the clinical relevance, biological variability compared to analytical variability, so you expect your analytical variability to be lower than biological variability. And finally, you can determine it on your instrument capability and technical limitations. And for this paper, we didn't have data on biological variability because no such study was performed as of yet, but we could only do it for instrument capability and technical limitations. But just to be sure, we did compare our technical replicates to this random sample set of population we used to validate our method. And as we can see, most peaks, which are greater in relative abundance, show our technical replicates in very, very thin lines, showing that our precision is much better than the rough estimate of a biological variation presented here in these graphs. So, in order knowing the limitations and of our instrument, and knowing that our analytical variation is likely lower than the biological variation, we landed on the following criteria. So, if the peak is relative abundance is over 3%, we want the coefficient of variation to be under 5%. If it's between 1 and 3%, then we want it to be under 10%, and if it's less than 1%, we want it to be under 15%. And that would be it from the paper on automation. The next paper I would like to touch on is the one we already heard a bit about, and it's about glycan stability and other types of precision. This one was done in collaboration with medical faculty of Osijek, Stanford University, mainly from Professor Snyder, and also Yuan University from Australia. We were happy to see that it was published in Gera Science. So first, we wanted to evaluate the short-term variation. So we analyzed students, 28 students, 9 male, 19 female, and we wanted to see how stable their glycans were in the period of 3 months. They were analyzed every month, and we found no significant trends in their glycans, even because we talked earlier that estrogen affects glycosylation. We stratified them according to their sex, and both sexes showed very stable glycomes in this period of time. When we look at the long term, this picture you already saw, and this is Professor Snyder. We can see that his glycome showed very stable trends. These trends follow the previously reported trends, but we also have 2 interesting points to mention here, and these are these 2 great falls in G0 and similar increases in G2. Similarly is followed for S, like G2, and for B. And what we knew from this is that this professor, he made some kind of intervention to try and lower his biological age. We don't know the nature of this intervention, but we can clearly see in Glycome that this intervention happened, especially because the trend keeps being the same, but you can just see a great increase or decrease depending on the trait you are looking into. So back to precision. You might wonder, again, why do we need all these types of precision? What kind of information do we get? And yes, repeatability is very important. It tells us how consistently our method can get the same result within a single run, but also intermediate precision, saying how precise can we get over periods of days or weeks. And even within run laboratory precision or reproducibility, when things change, when different operators change, when different reagents change, how good our method is at replicating the same results over and over. And according to standards provided by Clinical and Laboratory Standards Institute, the usual setup for this kind of analysis is doing a pentaplicate over 5 days or tetraplicate over 7 days. Our setup was more elaborate because we were using the Professor Snyder cohort. We used our standards we normally use to check the accuracy and precision of our methods. And we did it over 26 days, and we used it in tetraplicate. So that's why we have such elaborate setup for this kind of analysis. And the results are as follows. So we used 3 different standards to represent 3 different concentration points. Standard 4, Standard 5, and Standard 6. And the results are as follows. So Standard 4 performed the worst. So the ones highlighted in red, The peaks highlighted in red are the peaks according to the acceptance criteria we defined in the previous paper. So we wanted to see, even though it's not the same method and acceptance criteria is supposed to be defined by method, we wanted to see just how good this criteria will apply to other to this method, specifically to capillary gel electrophoresis method. And as we can see, again, so this is capillary gel electrophoresis, so it's a bit different than UPLC I showed you earlier. So now the sialic acids and more polar peaks come first, and the less polar one come later. And we can see that here, especially in the first peaks, again, the sialic acids have slightly higher variation, but as you go down, this variation becomes lower. Only peak 20 had constantly high variation across all three standards. So similarly goes for standard 5. Standard 5 performed much better. And here we can see peaks 2, 3, and 4 again showing high variation, peak 20 and peak 14. But the other peaks showed pretty great precision and would easily satisfy the criteria we defined earlier. And similar goes for standard 6. Here, peak 1 and peak 2 are the ones, the outliers, and again, peak 14 and peak 20. So what does this all tell us? It tells us that IgG glycome profiling, and by extension our glycanage test, is very precise, analyzing a very stable glycome, and it can be used as a tool for monitoring individuals' fluctuations in health and lifestyle interventions. And finally, I would like to wrap up with my conclusion, and it is these three things. So first, we talked about it a lot yesterday at the brainstorming. We need more standardization. We need to implement more good practices and practices from clinical settings that will be able to be applied. So our methods that we are developing, our potential biomarkers can be used in clinical settings. We also need to tackle accuracy. We have a dire need for standards because no analysis of precision will go, or no validation will go without validating accuracy. Because if you have a very precise method, but it's not accurate, it's not really helpful. And finally, we have a dire need for biological variation study, which will be able to, which should be performed by the standards of European Federation for Laboratory Medicine. And we really need this because having a good biological variation study will tell us how good and how important the changes we detect and how can they be translated to to people that are potentially analyzed. And finally, I would like to thank all my colleagues who helped me on this, and thank all the funding. And thank you. Yes?
Questions? Well,
thanks. Yeah, very interesting work. Thank you for that. And it sort of reiterates what I was getting at earlier today,
Yeah.
right? So, if I understood correctly, the PKIN robot actually performed inferior to the manual
Yes.
pipetting. So, a couple of questions. Number one, how many replicants did you run? Secondly, was the manual pipetting done by one operator or by several different operators? And thirdly, how do you interpret that?
So, let's start with the number. So we used 32 replicates, 32, across 2 plates. So it's not a lot. It's a very small comparison, especially when you're talking about automation. Automation should be performed on many more replicates because that's where its strengths lie. Also, we compared it to a single operator. A single operator who was doing only 2 analyses, they could concentrate and they weren't so tired, for example, if somebody would be doing many repeated analysis. And that's the whole conclusion of ours, is that yes, over a single run, probably person will be better because person will concentrate, person can check if something went wrong and can fix on a fly, fix the issue on the fly. But robots over multiple runs, over a long period of time will eventually surpass the person and be better.
Lovely talk, yeah, and it's really necessary. All these, they're not exactly sexy experiments, but it's needed for the lab. My question is about, it's kind of related to the last question. Is it liquid level detection that your TCAN is using, or is it fixed volume? Like, is that part of the issue?
So it uses fixed volumes, so we didn't use any liquid level detection.
Do you use liquid level detection?
Yeah, there is ability to use liquid level detection, but we were using the pre-dispensing.
Because we found in our lab, when we were using the fixed volume, we were getting higher variability. But when we switched to the liquid level detection, we could tighten our CV values. So it's just something to possibly look at.
Yeah, it's definitely an avenue we can look at, yeah. Thank you.
Okay, thank you.
Thank you.
Everybody.